Okay, so we're talking about bonding. This is the new chapter, new topic. And in order to understand chemical bonds, you need to understand how the valence electrons cause those bonds. So we spent chapter 4 and 5 talking about electron orbitals, electron configurations, and we're going to now apply that to the concept of bonding. So atoms would like to be in the lowest possible energy state. Lowest energy state means more stable. And you can remember when we talked about spectral analysis and the emission lines of atoms, when you excite the electrons of an atom, they go up to higher energy levels, but then they fall back down. And they want to be in the lowest possible energy level that they can be in, which is why you don't find an atom that has electrons in energy level 1, but not 2, and then in 3. Electrons will always be in the lowest energy level that they can fall into, that they can be in. The atoms want to be as stable as possible, which means the lowest possible energy state. And so an atom that has 3 or 4 or 2 or 1 electrons in its outer shell, in the valence electron shell, is less stable than an atom that has a full valence shell, that has all 8 electrons filled in its outermost level. And so the atoms want to seek that state. They don't actually have a will and a desire. We kind of personify them when we say this, that they want to have 8 electrons. They don't have a brain and a soul, and there's no desire in the atom, right? But they behave in such a way that they will seek out an orientation that has 8 electrons in the outermost level, so that outermost level is full. And an atom would rather be bonded to another atom, and between the two of them have full energy shells, than to be by itself with an incomplete energy shell, an incomplete energy level, right? So this is all going to be about the valence electron shells, the outermost energy level. And we're going to be looking at how they find the more stable condition. Whenever they can be more stable, they will be more stable. You will never find an atom that could be more stable if it bound with another atom and have these two atoms not bond, right? They don't have favorites. They don't say, oh, you smell, I'm not going to be your friend. Atoms will always seek out, when possible, the lowest energy state, the most stable energy state. And if they can pass electrons back and forth and get there, it'll happen, which is what makes chemistry predictable and reliable, and that is part of God's design, that whenever reactions can happen, they will. You don't have to wonder if this is going to occur, right? And so when we're talking about energy, we're looking at the energy state of compounds. Remember, things at the beginning of a chemical reaction we call reactants, and things at the end of a chemical reaction we call products. And reactants tend, in most circumstances, to have more energy in them than the energy that is in products. So to go from a reactant to a product is a downhill process most of the time. And so the reactants will react in a chemical reaction to produce products because this is a lower energy state, this is more stable. The difference, or the slight exception to that, is that in order to get a chemical reaction to happen, you usually have to add energy to get it to happen. You put two things in a test tube or a beaker, and you have to stir it to add a little kinetic energy, or you have to heat it up to add a little thermal energy, or something of that nature. You've got to get a little energy in there first, which we call the activation energy. We'll get to that later. Don't worry about writing that down right now. But reactants have to get some energy added to them, and then the reaction can happen, and then it flows down to the products, right? And the products tend to be more stable and have less energy in them than the reactants do. Okay, so we're looking at things that make chemicals land in a lower energy state. The main idea that governs this is called the Octet Rule. For the huge majority of atoms that we're going to deal with in this class in chemistry, atoms seek 8 electrons in their outermost shell. Okay? The transition elements don't want 8 in their outermost shell, but those transition elements don't tend to react very much anyway, and they are going to be pretty much ignored in your high school level chemistry class. And so we can kind of forget that they exist for the case of the octet rule. Most atoms that you will deal with in high school chemistry are looking for 8 electrons in their outermost shell. There are some exceptions to that. We'll deal with the exceptions, but this is the rule most of the time. And so because they're looking for 8 electrons in their outermost shell, we call it the octet rule. Oct is 8, so this is the rule of 8. And this is true for any main group element, the things that are in the S or P blocks. Transition elements and the F series don't follow that rule, but again, we don't play with those very much. So for the main group elements, they want 8 electrons in their outermost shell. Okay, so I feel so lonely. It's like I'm incomplete. Here we have an atom that only has 3 electrons in his outermost shell, right? He would like to have 8. How can he get 8? Well, he can either gain 5 more, or he could lose the 3 that he has right now, and then expose the layer underneath this one, which would be full. Okay, so depending on which way an atom needs to go to get 8 electrons in a full valence shell, they can either ditch the electrons on the outside and so show their complete shell underneath, or they can add more electrons to the empty shell to get up to 8. Okay, so atoms are seeking 8 electrons in their outermost shell. If we look at a periodic table and only look at the main series elements, okay, then we have the S block and the P block, and you can see, we've already covered this, that in the S block there's 1 electron in the outermost level. In the second family, there are 2 electrons in the outermost level. 3, 4, 5, 6, and 7 will have 3, 4, 5, 6, and 7 electrons in the outermost level. And the noble gases out here are full. They have 8 electrons in the outermost level. So if everybody is trying to get to 8 electrons, everybody is trying to be like a noble gas. And that can help you remember it, right? Everybody would like to be noble. Wouldn't you like to be noble? I would like to be noble. Once upon a time, my ancestors were noble, and then they lost it, and sad for them. And I'm no longer, a prince of France. But nobility is something that atoms are seeking, right? They're desiring some kind of nobility. So they would like to have 8 electrons in their valence shell, just like the noble gases do. So fluorine only needs 1 more electron to get there. He would really like to find a way to get 1 more electron, and then he could be like neon. And that's what he wants to be, just like neon, right? But lithium has only 1 electron. It's going to be really hard to pick up 7 more. So lithium would much rather just ditch the one that it has and expose the full energy level underneath. And then it would have a full energy shell to show the world. So lithium is walking around like, hey, anybody want this stupid electron? Can I please sell this to you? Would you just take this from me? Here, look, I won't look and I won't call the cops. Just take the electron, please. And fluorine is saying, hey, give me that electron. I would like electron. Can I have electron, please? Anybody want an electron? I got electron deep in my soul, right? So the closer you get to the middle of this block, the more there are atoms that are not quite as motivated to react. Fluorine and francium is not even on here. Francium is down here. But fluorine and francium are the 2 most motivated elements in the world to react. Francium will violently give you his electron, right? He doesn't ask if you like it. He walks up, shoves it in your face, and walks away, okay? Francium wants to get rid of his electron like nobody's business, and fluorine has frequently been in jail for stealing your electron, right? Those are the 2 most reactive elements on the table. As you get more to the middle, especially in the transition elements, they're like, yeah, I could react or not, these guys, we're going to talk about covalent bonding in a minute. These guys tend to covalently bond, whereas these guys tend to ionically bond, and we'll get to that in a little bit. But you can see how the valence shell orientations tend to control that, okay? So the octet rule, again, you don't have to write this down, you've already got it. Atoms tend to gain, lose, or share one or more of their valence electrons to achieve a filled outer electron shell. That's the main idea here. And somebody else said, in chemical compounds, atoms tend to have the electron configuration of a noble gas. That's another way of thinking about it, right? They all want to be noble. Make me like a noble gas. There's two ways to get this done. Take a moment to write this down. So, we've got two ways to get to 8 electrons in the valence shell. One of them causes what's called an ionic bond. One of them causes what's called a covalent bond. There are some other ways of bonding too, but for the sake of this lecture, we're going to look at those two as the main examples of how a bond forms. The first one is give and take. It's the ionic bond. An atom with electrons to give pairs with an electron that needs more, exchanges electrons, become ions, and are attracted to each other as a result. Okay, so I gave Renee 6 M&Ms. I gave Hannah 2 M&Ms. We're going to pretend that they're electrons for a moment. Okay, Renee and Hannah both want to have a full outer valence shell. Renee has 6. She needs 2 more to look like a noble gas, right? She needs 2 more to look like a noble gas to have 8 on the outside. Hannah only has 2. Odds are Hannah's not going to find 6 more. But underneath her electron shell that only has 2 valence electrons, there's a full energy shell underneath that. So she could look like a noble gas if she got rid of her 2 extra electrons. So ionic bonding, what's going to happen is Hannah is going to give Brene her 2 electrons. Now Brene's happy. Look, she just smiled because she looks noble. Brene got to look noble. She has 8 electrons now. And Hannah, even though she doesn't have any M&Ms on her table, Hannah also looks noble because she got rid of her 2 extra electrons, and now the full shell underneath is exposed. Both girls are happy. They both look noble. Yay! And what else happened? Well, Hannah got rid of 2 sources of negative charge, which means what's Hannah's charge? Positive 2. And Brene accepted 2 sources of negative charge. So what's Brene's charge? Negative 2. What would happen to a positive 2 thing and a negative 2 thing? They're attracted to each other, right? Now, let's not get weird, okay? Brene and Hannah are not attracted to each other, okay? But they're atoms, right? No, so they are attracted to each other, and now they have bonded, right? Do you guys feel bonded? No, see, they bonded. It's great. And now that they've served this example, I'm going to let them share their M&Ms, and Brene doesn't have to eat all 8, and Hannah doesn't have to eat, none. But they can have their M&Ms. So 2 atoms become opposite charges by exchanging electrons, and because of that, they're attracted to each other, and they bond. So here's a picture, a moving picture. Sodium gets rid of its extra electron and gives it to chlorine, and now the positive and the negative are attracted. Okay, so the extra sodium electron goes away, and it lands in chlorine's world, and now chlorine is negative and sodium is positive, and they are attracted to each other, and you have table salt, sodium chloride. Okay, so that's one example. Here's another one with dogs, because everybody likes dogs. We have a dog that has an extra bone and a dog that wants that extra bone, and they get into a little fight, and the one dog winds up with 2 bones, and the other one has no bones. It's sad. And the chlorine now, represented by the big dog, is negative because he has extra electrons, and the other dog is positive because he has no electrons, and they are attracted. So if you like the actual picture where the dog's better, however you want to think of it, either way, that's the way ionic bonding works. Here's covalent bonding. Take a moment to write that down. So the other way to make a bond is covalent bonding. Covalent bonding has 2 atoms, 2 atoms satisfy the octet rule by sharing enough electrons that they both have a full valence shell. So This tends to happen with things in groups 3, 4, and 5, typically. And an atom that has 3 electrons in its outermost shell is probably not going to find another atom to give 3 electrons to, and is probably not going to find another atom to steal 5 electrons from. But it could share some electrons with another atom that needs some more. And they will both look at the electrons together and say, that's mine, and it's yours. And, ooh, now we have so much more, right? And they're sharing them between the two. So, as an example here, I gave Steph 4 M&Ms, and I gave Cody 4 M&Ms. Neither of them are going to find the ability to give or take 4 more electrons. An atom's just not going to give up that many. But they could share. So what's going to happen is Steph and Cody, put your piles of M&Ms like right next to each other. And now pretend that those are all both of your M&Ms. So Cody, how many M&Ms do you have? 8. Oh, isn't that cool? Steph, how many M&Ms do you have? 8. They're both happy. And we didn't have to create any more electrons here, right? They're just sharing. And so because they're sharing, they both feel happy inside. And they both feel like they look noble, even though in truth, they only look half noble. But that's okay. They're both sharing enough electrons that they have satisfied the octet rule, okay? And so by doing so, they've created a covalent bond. You guys can now share your pile of M&Ms there. There you go. So here is an example. These 2 atoms, neither of them are full. They both need 1 more. This would be like fluorine and fluorine, or something of that nature. They both need 1 more electron. But when they bump into each other in the right way, they share their 1 random unpaired electron. And so now they are both looking at both of their unpaired electrons. And they both feel like they have 8. And so that is an example of a covalent bond. They both feel like they have 8. And that bond is called covalent. Okay? And again, we like dogs. Dogs are fun. So, oh wait, I've got another picture before the dogs. Just a second, we'll get to dogs. Water molecule. Oxygen has 6 electrons, hydrogen each have 1. If the hydrogens share their 1 electron with oxygen, now they are full. Remember, hydrogen only has room for 2 electrons. So he's full with 2. So would helium be full with 2? Everybody else needs 8. Hydrogen here shares with this other random unpaired electron from oxygen, and you have 2 and 2 and 8 when they all look at their electrons together. So these are shared, and the water molecule is a covalently bonded molecule. Oxygen feels like it has 8, hydrogen feels like it has 8. They all feel noble. Or sorry, hydrogen feels like it has 2, right? They all are satisfied. More. So phosphorus comes to the table with 5. Chlorine comes to the table with 7. If 3 chlorines share with 1 phosphorus, everybody feels full. Everybody feels like they have 8 electrons. Okay? We just did the water molecule. Carbon dioxide is another example. Carbon comes to the table with 4 electrons. He would like 4 more. Each oxygen comes with 6. These guys now share 2 sets of electrons each. This is a double bond, a covalent double bond. Okay? So carbon and oxygen are double bonded. This carbon and this oxygen are double bonded. Carbon now feels like it has 8. Oxygen feels like it has 8. And everybody's happy. All right? Now dogs. Okay. So here we have 2 dogs that would both like 2 bones. And they wind up sharing 2 bones each. Okay? So that would be a covalently bonded chlorine molecule. You guys understand the idea? Okay. Okay, so we just previewed this in the last slide's examples, but you can share only 1 pair of electrons, and that's a single covalent bond. Or you can share 2 pairs of electrons, which would be a double covalent bond, and it is possible to share 3 pairs of electrons, which would be a triple covalent bond. The more pairs of electrons you share, the more stable the bond. So it's easier to break a single bond than it is to break a double bond or a triple bond. You can also think about it as the amount of energy that would be released if you broke a single bond is less than the amount of energy released if you break a double bond, or the amount of energy released if you break a triple bond. Which is why some of the very high temperature burning fuels like acetylene is a triple bond. Because when you finally get that very stable triple bond to break, you release scads of energy. Okay, that's why acetylene torches are very, very hot. So single, double, and triple bonds, the more pairs of electrons they share, the more stable the bond. Okay, so pictures. Here we have a double bond, 2 oxygen atoms. Looks like an owl staring at you there, but 2 oxygen atoms that each come to the table with 6 electrons. They both want 2 more to be full and have 8 electrons in their valence shell. One oxygen says to the other, I could give you 2, but then I would only have 4, and that would make me sad. And the other oxygen says, well, same for me. And they said, but we could share. So the one oxygen says, here's 2 electrons that I can share with you. And the other one says, oh, here's 2 electrons I could share with you. And now they share these, and now they both look like they have 8. And they feel happy inside, right? Because they look noble. So these oxygens are sharing 2 pairs of electrons. That is a double bond, more stable than a single bond. Here is another way of looking at a double bond. This takes into account electron orbital shapes. They're sharing 2 electrons from an S energy level, and that the spheres that are close to the nucleus, right? So they overlap in the S level, and they call that a sigma bond. And then the P are these, like, remember, Q-tip shaped things that look kind of like balloons. And they're going to overlap P orbitals. And when they overlap, they're sharing electrons there. This is sometimes called a pi bond because it's with the P energy levels. And so sigma bonds and pi bonds are ways of drawing how these electrons are being shared. Okay, so this is an example of a double bond. That's another way of drawing a double bond, where you just put 2 lines between 2 atoms and say those 2 carbons are sharing 2 pairs of electrons. So here it's sharing a single pair of electrons with this hydrogen, another pair of electrons here, and 2 pairs of electrons with this other carbon. So this carbon has 2, 4, 6, 8 electrons that it either owns or is sharing, and it feels happy. Each hydrogen is sharing 2 electrons. That's as much as it needs. It feels happy. This other carbon is the same way. So everybody feels noble, and we have a nice double bonded molecule here. Okay. Triple bonds. Let me move my video picture down here for just a moment. So triple bonds, the carbons are sharing here the sigma bond, and then the pi bond, the p orbitals are overlapping, and we can share another set. I think I have that here. Yes, we can share another p orbital set. So then it's sharing the sigma in the middle, and it's sharing this pair of electrons, and then another pair of electrons, so that we have here a triple bond. Triple bonds are always going to make a straight molecular shape. Okay, so in this particular example, this would be acetylene, 2 triple bonded carbons that have a hydrogen on the outside here, C2H2. And this is a very high energy bond, and if you do break it, it releases tons of energy. Okay, and the last kind of bond is metallic. And I'll go ahead and keep talking while you write for the sake of time. The third way that you can bond is a metallic bond. A metallic bond, metal atoms share their electrons widely, and they don't really care if they always have 8 valence electrons. Because remember, they have outer D shells, not outer P shells. And a D takes 10 atoms to fill. And they're not going to get 10 electrons at any one particular time. And so metallic bonds are formed when electrons are just passed back and forth between atoms all the time. And maybe for a split second, an atom can look at 10 electrons, and then it'll feel happy. But it's only going to happen for just a moment, and then his electrons are going to get passed on to somebody else. This is what makes atoms good electrical conductors, because electrons flow throughout a piece of metal. Electrons are being passed around all the time. So electricity can flow through a piece of metal. Electrons can jump on one end and kick electrons off the other, and nobody really cares. Metal atoms pass electrons back and forth across the whole piece of metal. So their individual deficit or surplus doesn't matter. And I put down here communist atoms, right? One little atom says, I don't have enough electrons. And another atom says, I got a few here. And then that one says, oh, but now I don't have enough electrons. And another atom says, I got some, here you go. And they keep passing it back and forth. And really, truly, nobody is full, which is kind of the way it works in communist countries. Nobody really has enough bread. But if we keep sharing it rapidly enough, we'll all pretend that we have enough bread, right? And so to simulate this, I gave Sarai 3 M&Ms, I gave Celeste 4 M&Ms, and I gave Abraham 5 M&Ms. Guys, I want you to pretend you're 3 metal atoms. And just pass your M&Ms individually back and forth amongst each other all the time, rapidly. Passing in, passing. That's kind of what metal atoms are doing all the time. Maybe for just a split second, there might be eight M&Ms on somebody's plate. But just for a split second, after that it goes back away again. And nobody really is noble. But we're all going to be so proud of our sharing that we feel good anyway. Okay? Thank you very much. Thank you very much. Do you guys understand the idea? Yeah. Ionic, covalent, and metallic. If you have any questions, let me know. And that will be the end of it. You can get your cover sheets out.